All right, it is 2:05. We're gonna go ahead and start now. Hi, my name is Prabuddha Dastidar.
And I'm Connor Mitchell, and we are both high school seniors at the North Carolina School of Science and Mathematics in Durham, North Carolina.
Today, we'll be talking a little bit about fused deposition modeling 3D printing in invasive cardiology. So FDM has numerous applications in invasive cardiology. Firstly, so this cardiovascular system is full of cylindrical or near cylindrical structures. It is quite common for individuals to struggle with health issues involving obstructions to these cylindrical structures. For example, arteries could get clogged with plaque, which is a mixture of fat, cholesterol, and waste. Heart valves could fail due to chronic disease or gradual loss of function, and all of these issues obstruct and disrupt blood pathways in the body, and therefore they could be extremely fatal. To combat these issues, prosthetics and medical devices have been developed to restore function to blood pathways, such as stents, such as arteries or blood valves. However, there are numerous pitfalls in the manufacturing of these medical devices, leaving potential for increased affordability and efficiency. Here, fused deposition modeling 3D printing could be of insurmountable importance in solving these issues. It is often overlooked for its simplicity, but when applied with innovative motion systems as we have done, FDM 3D printing can be a powerful tool, especially in the stent manufacturing industry. In the upcoming slides, Connor and I will discuss the shortcomings of the stent manufacturing industry in extensive detail and our invention to combat these shortcomings. We have fabricated a stent 3D printer. And before I like to move on, I would like to note that our invention is just one example of how fused deposition modeling can be applied, not only to invasive cardiology, but also to other fields of medicine. So stents are manufactured to alleviate pathways in the respiratory, gastrointestinal, urinary, and cardiovascular systems, and therefore potential for FDM printing is plentiful across several medical fields. So now a little background about stents. A stent is a mesh tube inserted into the opening of a blood vessel in order to keep the passageway open and prevent a blockage. Stents are quite common, as over 2 million Americans undergo a stenting procedure every year, and this is just for coronary arteries. Post-stenting complications are also quite prevalent, as the risk of re-narrowing of the artery is 10 to 20%, and the risk of the artery clogging after stent placement is approximately 5%. Numerous studies have been conducted by accredited institutions such as Mayo Clinic to confirm these statistics. And these complications can be extremely deadly and lead to conditions such as restenosis or heart attacks. So now we'd like to discuss a little bit about the stent manufacturing industry. So the most common stent manufacturing methods are laser machining, die casting, and micro EDM. And these all have very significant shortcomings. First of all, these units can cost above $100,000. Next, they follow a one-size-fits-all approach with their stents. So the stents may not fit the patients very well since they're one-size-fits-all, and this could lead to complications. For instance, a stent could not fit a patient very well and get lodged in the artery walls, and this could lead to blood clots. Furthermore, all of these methods must be completed off-site due to the extensive capital and infrastructure which they require. And in the industry right now, the most significant innovation is a PBF, powdered bed fusion 3D printer. However, this is incredibly flawed as it is far too expensive and it requires very extensive infrastructure and capital as seen on the image on the right, which is actually a PBF 3D printer by CSIRO, an Australian research organization. So for this, we have developed the Theta Zero, an innovative, affordable approach to the on-site rapid 3D printing of artery stents, parameterized to fit individual patients' needs. The Theta Zero addresses each and every one of these industry shortcomings that we discussed in the previous slide. It is extremely innovative as it's a 3D printer with a novel motion system that is specifically designed and hand-built from scratch for printing small, complex cylindrical structures such as those of stents. It is extremely affordable as it costs $471 per unit, and when it's brought to scale, that cost could be driven down. And 10 to 15 cents in materials cost per stent versus hundreds of dollars for stent in the industry. And these hundreds of dollars for a stent in the industry doesn't just account for materials cost, it accounts for labor and all of the extensive capital and infrastructure behind the manufacturing as well. This is a simplistic FDM or fused deposition modeling system of the R-Theta0. It takes up less than 3 cubic feet, having a very small footprint, so it can be available on site, unlike anything else. Additionally, stent can be printed within 2 hours of parameter input and can be customized with the RGen software, which is a novel software that we developed. So basically, a doctor can input stent parameters in the user interface of the RGen software, and then this will convert those parameters into machine code or G code that is specifically formatted for our motion system, and then a stent will be delivered within 2 hours.
So the next question is, how are we able to accomplish all of these objectives? Specifically, how are we able to get the necessary quality with parameterization at an affordable rate? Well, in order to attain the affordability factor, we implemented fused deposition modeling, which is a simplistic and affordable method of additive manufacturing. However, then we needed to worry about getting the necessary quality. And for that, we implemented a polar motion system, which is a revolutionary motion system consisting of R, theta, and Z axes. Now, a traditional Cartesian printer, which contains X, Y, and Z axes, would require the perfect coordination of the X and Y axes in order to print the circular geometries of artery stents. And due to the actual scale of artery stents, all inaccuracies and mechanical slop are going to be magnified greatly on a Cartesian system, contributing to increased ovality and stent deformation. We were able to solve this, however, by implementing the polar motion system, which requires no axial synchronization for circular geometries and only the actuation of the theta axis. And it minimizes the effects of mechanical slop. All of this combined allows for greater print quality.
What we're saying is that this is a completely novel application of FDM or fused deposition modeling printing. Firstly, it is the first time that a dual extrusion system has been implemented on a polar motion system for 3D printing. Also, it is the first time that there's been a horizontally static print bed on a polar 3D printer. Now, this causes an extremely increased axial rigidity and the complete elimination of cantilevered axes, the way we've developed it. And then we have dual extrusion, which help prints complex stent designs, and the static print bed, and the elimination of cantilevered axes and axial rigidity, which help increase accuracy and precision of the print to a point that could not be previously achieved with polar 3D printing. Additionally, we developed a novel RGen software or code or machine code directly generated from stent parameters for a streamlined user experience. So once again, a doctor can just input stent parameters into the software and receive a custom fabricated stent within 2 hours of input.
Okay, so now we're going to talk a little bit more about the actual mechanical design. Now, there are 3 main axes, as we mentioned before, the R, theta, and Z axis. Now, the first of these is the R axis, or the radial axis, which contains the R carriage. Now, it is supported by 2 horizontal steel linear rods, and the carriage's center of mass has been designed such that, or the carriage has been designed such that its center of mass is centered between them in order to minimize resistance. Additionally, the R carriage contains the printer's hot end and nozzles through which the molten filament is extruded in order to generate the printed part. Now, we've designed the entire thing such that the actual frame or the actual parts and components of this carriage are both PLA and PETG 3D printed parts, in order to decrease the weight and enable the ease of manufacturing of this actual component. Additionally, we implemented a Bowden configuration, which means that the actual motors, which are in charge of propelling the filament through the extrusion system, are actually mounted elsewhere on the printer. This helps to decrease the actual weight of the axes, in turn allowing for increased speed and, more importantly, increased quality. So next we have the Theta Carriage, and this is my personal favorite part of the printer. So the Theta Carriage is used for theta axis actuations, as you might expect, and is belt driven by a NEMA 17 stepper motor, though we do plan on upgrading this in the future, and it has a 476/20 reduction, which greatly increases the axis's precision. Additionally, it is supported by 8 V-groove bearings, and we've actually allowed for 6 of these to be tensionable in order to allow for greater carriage security. And then, as mentioned before, as part of the Bowden setup, the actual extruder gearboxes are mounted within this carriage, where they can be mounted in a much easier manner. And then, last but not least, we have the Z carriage, which moves along the Z-axis with the progression of the print. Additionally, it houses the heated print bed, which has been made horizontally static in order to eliminate the forces that are placed on printed parts, from the bed constantly accelerating as part of the axis, which is a common yet flawed technique in FDM printing. Additionally, due to the fact that the bed is horizontally static, we are able to implement the fact that I mentioned previously, where the theta axis is allowed to be constantly tensioned and centered using the adjustable V-groove bearings. If we had not implemented the horizontally static axis, then we would have to worry about some of the actuations or some of the movements that are caused in zeroing that axis.
So I'd like to talk a little bit about the dual extrusion. The R-Theta0 also has hardware support for dual extrusion printing, which allows the printer to print two materials simultaneously from two different nozzles. It contains two separate hot ends, which allows different heat settings to be used for each nozzle. This allows it to print not just simultaneously from two nozzles, but with two completely different polymers. The first of these, which we plan to print with, is TPU, or thermoplastic polyurethane, which comprises of the flexible body of the stent. And the second material is PVA, or polyvinyl alcohol, which is a soluble support material that dissolves when it's placed in water. So basically, the TPU is printed and molded on top of the PVA as it's printed, and the final composition is a TPU PVA mix, which then, when it's dissolved in water, the only thing that remains is the TPU, and this allows for more complex stent mesh geometries, in turn enabling the fabrication of more complex stent designs, including drug-eluting stents, which I'll discuss in the future directions.
Okay, so now a little bit about the software and the firmware that operates the printer. So the R-Theta0 has two major software elements. The first of these, RGen, is the slicing software which is responsible for converting CAD models into G-code or machine code. However, because there's no available polar slicing software, we developed RGen completely from scratch, and even streamlined the process by taking a stent parameter input instead of a CAD model. Right, and this helps to eliminate the step of actually needing to generate that CAD model from the user operations, in turn simplifying the process further. So next we have RGen, which consists of the front-end graphical user interface, which allows for the input of stent parameters with ease, stent dimension rendering, and G-code rendering within the RGen slicing software when prompted. All of this combined helps to make it as simple and efficient of a user operation process as possible. And then the final element of the software is actually the printer firmware, which is responsible for delivering an electromechanical response to the G-code commands. Together, these two elements allow the R-Theta0 to fabricate customized stents in well under 2 hours. One thing I will note is that for the firmware, instead of developing it from scratch, we've actually taken a modified version of the open source and very popular within the field Marlin. And then another thing is that the question of how are we actually transferring that G-code to the printer itself, to the printer firmware, to the printer mainboard. And we're doing this in one of 3 ways based off the printer's make and model. The first of these is we have the option of transferring that file manually via a SD card. The second option is transferring that file wirelessly from RGen to the mainboard, and that would be via Bluetooth or Wi-Fi. And then the third option, which we are currently working on developing, is making it such that that RGen software would actually be implemented locally on the printer. And this would eliminate the need for an external machine altogether, and it would just automatically run all the software, all of the G-code directly to the mainboard.
So now on to the output of the actual printer. With all of these technical specifications that Connor and I talked about, stent quality is not compromised, as the R-Theta0 is capable of printing stents with extreme accuracy and precision. The outer diameter can be as low as 2 millimeters, and stents can be printed with 15 micron total precision with reasonable slop, which are great numbers for the industry. And we do plan to build future iterations of the 3D printer where we modify things such as the Theta Carriage, which Connor will talk about later, and that will be able to drive these numbers down, resulting in increased accuracy precision. Additionally, all of the stents are biodegradable or bioresorbable, as they're made of the polymer thermoplastic polyurethane. So why does this help? Stents are not needed for the entire lifetime. So by reducing the amount of time that the stent is in the body with the bioresorbable stent, you can actually reduce the probability of post-stenting complications such as restenosis or heart attacks. So in other words, the stent only stays there for the amount of time it is needed to restore blood flow to the artery. And after that, the stent is consumed by the body, Yeah, as it's biodegradable, eliminating the risk of post-stenting complications after that. And of course, once again, all stent parameters can be very easily customized using the RGen software.
So now a little bit about the testing and the results of the printer. So we have carried out mechanical and quality testing on all parts of the R-Theta Zero, and then we have even revised each and every one in order to optimize functionality. Additionally, every subsystem has been proven to be mechanically viable through both mechanical motion testing as well as repeated software testing through G-code that was developed by the RGen software. We've actually put so many revisions into this that not only have we revised and iterated on every component of the printer, but we have even reiterated on both the software and even the full electrical layout. In terms of precision, we have some incredible precision. The first of these is the R-axis, which has similar precision to the X-axis of a traditional FDM printer. However, due to the nature of the geometry of these stents and the actual effects of polar printing, the impact of that R-axis precision error is considerably negligible, right? And then additionally, the theta axis has a predicted precision of an incredible 2 microns, which is over 60 times better than that of the comparable y-axis of a standard 2D. And then finally, the z-axis, while it has comparable precision yet again to that of a more traditional FDM printer, it is due to the impacts of the nature of how these geometries are working, as well as the large quantity of axial rigidity we have introduced into the z-axis. We figure that the impacts of the actual z-axis slop will be much less than in a more traditional FDM printer. Okay, so now a little bit about the future directions of the printer. What are some of the changes and developments we would like to make? First, I'm going to talk about some of the things from the engineering side. So the first thing, and the part that I'm quite excited about, is we want to implement software support for our current dual extrusion hardware system. Prabuddha talked about some of the impacts that this would be able to have. However, we have not yet been able to implement the support for this into our RGen software, and we're looking forward to being able to do this in the near future. The second thing we want to do is we want to further optimize the printer as much as possible. We want to run as many different test cases as we can against it, and then further, we would like to work on making sure we can get as much precision as possible, see if we can get even greater precision than we've already been able to observe. And then lastly, we are working on the current design and development of an R-Theta Zero production unit, which would work to maintain specs that are much comparable to those much more comparable to the industry in terms of the printer's composition, and would also make it easier to deploy. Some of the changes we are making there are we are substituting the current acrylic frame for a new sheet metal frame, which would lead to greater rigidity as well as longevity for the printer. Additionally, we're hoping to optimize the efficiency of the theta axis in order to both reduce costs and to reduce manufacturing time. Some of the changes we are making here are that, one, we are going to replace the current tensionable V-groove bearing setup with a more consistent 8.5-inch complete bearing. And then also, we are going to be looking at a change in the actual composition of some of the motion systems within the theta axis, again, to just increase rigidity and printer longevity. And then lastly, and I mentioned that we're working on developing this, is implementing RGen locally on the R-Theta Zero. All in all, these changes, we expect to take the printer from a base hardware and production cost of $365 to the $471, which we had projected previously. And now I'm just going to play a motion animation of the printer itself. This was created in Blender, if anyone's interested.
So now I'd like to talk a little bit about the future directions on the medical side of things. So I mentioned previously that the first material we plan to print with is TPU, thermoplastic polyurethane. So we want to assess the biocompatibility of this stent material with lab tests. And we have good reason to select this material and good reason to conclude that it would be biocompatible and biodegradable already, because some of its sister polymers that are very close in composition with it, are PCl, polycaprolactone, and PLA, polylactic acid. However, we would like to do these tests to confirm PCl and PLA in and of itself are extremely biocompatible and biodegradable as proved by lab tests previously. But lab tests have not been done on TPU. So what we'd want to do is we'd first want to conduct tests on a model fibroblast cell line, because fibroblast cells are stable and have a rapid growth kinetic. So they would allow us to get an accurate growth model and an accurate growth graph. Next, we would like to conduct testing on human epithelial cell lines for more realistic conditions. And testing on both cell lines should be done in static conditions for first a proof of concept, and then dynamic conditions in order to ensure realistic feasibility. Furthermore, we would love to utilize our existing dual extrusion software for more complex stent designs, such as drug-eluting stents, as I mentioned before. So these are stents that basically have drugs built into their pockets, and they elute drugs from their pockets into the arteries. These could be drugs that reduce inflammation in the artery. These could be blood-thinning drugs, or any of these types. And drug-eluting stents generally have more complicated designs since they have to hold pockets for drugs in their walls, and dual extrusion could be used to do this. And we could print more complex stent geometries as well, such as those seen in the right, some of which are drug-eluting stents. Furthermore, I mentioned PCl and PLA as sister polymers to TPU, polycaprolactone, and polylactic acid. We would love to extend the print materials to these polymers because this would introduce further stent customizability in stent rigidity, flexibility, and the degree of biocompatibility. These materials are slightly different in composition, so they have different factors, and it would allow us to parameterize the stents even further. For example, for a coronary artery, you'd want more stent flexibility since it's a smaller artery, and therefore you might opt for TPU, thermoplastic polyurethane. However, for example, for a femoral or for the carotid artery, there's heavy blood flow there, so you would want more stent rigidity and less flexibility. So you might opt for a material like PCl, polycaprolactone, or PLA, polylactic acid. And these just allow us to introduce further degrees of customizability in stent parameters. So in conclusion, the innovation of our invention, the R-Theta Zero, allows us to envision a future where doctors can use current medical scanning techniques to image a patient's arteries and receive a custom fabricated stent available for use well within 2 hours of parameter input, and this is all possible under $500. Thank you very much. So for acknowledgements, we would like to thank Dr. Tamar Abenary of the North Carolina School of Science and Mathematics for her invaluable mentorship and guidance when writing the research paper. Her support has been valuable to us, and this project would not be possible without her.
We would also like to thank Mr. Sam Durrani and Hangar 6 for making all of this possible by supplying access to the machinery and resources that were necessary to fabricate and prototype the R-Theta Zero.
I would like to thank Dr. Kaushik Chakrabarty and Chakrabarty Lab at the University of North Carolina at Charlotte. So he's the reason I got involved in biology research in 8th grade, and he provided the foundation for me in biology research for me to carry forward and work on projects like this, like the R-Theta Zero.
And then I would also like to thank Mr. Marshall Massengale and Ms. Meg Massengale for their support of me and also for their guidance in the development of this project.
And we would both like to thank the North Carolina School of Science and Mathematics for fostering a collaborative environment of innovation and for all of their support. So now we would love to take any questions about the project, any questions about the industry, any questions about anything you heard today. And you can just chat them to us, or I think there's a Q&A feature, and we will keep our eyes peeled for any questions. Do we have any questions? You may use the Q&A field if you have any. Or we'll just wait 2 more minutes until 2:31, and if we don't have any questions by then, thank you everyone very much for your time. Oh, it looks like we do have a question, Connor. What are the next steps that we have moving forward? Answer it live. Okay, so we have numerous next steps planned moving forward on the engineering and the medical side. And Connor mentioned that we would like to build some future iterations. So would you like to elaborate a little bit on that first?
Yeah, so one of the main things and one of the things that I'm most excited about is we're working on developing an actual production unit for the printer. The main current design is an acrylic frame. It has a lot of 3D printed parts, and while those are really good for testing, they wouldn't necessarily be good in an industry environment. So some of the things that we are changing are we are redoing the entire frame with a sheet metal frame that should hopefully increase the longevity as well as rigidity of the printer. A lot of the 3D printed PLA and PETG parts that make up the printer, we're going to be looking into possible injection molding as well as some SLA resin 3D printed parts. Again, so we can get slightly higher precision as well as greater longevity for those parts. And then other things we're looking for from the software side of things, we're looking at implementing some further dual extrusion support as well as support for other features with Indeed Printer from a software perspective. And then one of the other things that we're looking at is increasing the availability for how the actual operation software of Archen could be implemented. So currently we have it such that it is set up where you would do a manual file transfer from a remote device. However, we're looking at also setting up a wireless transfer of those G-code or those stent files, as well as a transfer in which the code or in which the software is actually running directly on the printer. And then it would just send it directly to the main board. And that I think is going to be a very popular option, simply because it eliminates the need for an external machine altogether.
So by perfecting the mechanics and the software, we're really going to hone in on the basis and the framework of the printer. So the next step is to get it medically accredited with medical tests on the stent materials, such as TPU. And for that, we'll be conducting biocompatibility tests, as I said, on fibroblast cells to get a growth model, and then human epithelial cells for realistic conditions. And then the next thing we'd want to do is we'd want to increase the print materials from thermoplastic polyurethane to multiple print materials so we can introduce stents for multiple arteries in the body. And also, we would like to utilize the existing dual extrusion hardware for more complicated stent designs that could help, for example, be drug-eluting stents. And also, one thing which I didn't mention in my future direction slide was that since this webinar is focused on invasive cardiology, but actually we could extend this to fields past cardiology. For example, stents are needed to alleviate pathways in the respiratory system, the urinary system, gastrointestinal system as well. Basically, for example, in the respiratory system, if there's a tumor in the respiratory tract, then a stent could be used to open up the respiratory pathway. And then for the gastrointestinal system, to prevent any blockages, there could be a stent inserted into the esophagus, for example. And in the urinary system, stents could be inserted into the ureter. And these stents have the same basic design as artery stents. So, and the manufacturing industry for these stents have the same basic flaws as the manufacturing for artery stents. So therefore, we could use this concept and apply it to other fields of medicine as well. Thank you very much for your question. Great question, by the way. Oh, I think we have another question, Colin. Okay. This is an interesting innovation. How long did it take to design and build this device and its software? So the inception of this actually occurred when in in October, when we were hallmates at the North Carolina School of Science and Mathematics. Connor and I were playing a game of pool, and he was telling me about an innovative motion system for 3D printing. And then over the course of the day, I actually thought of applications of this motion system and ways to take this motion system and modify it so that it's best for stents. And I approached him with this idea to use the motion system that he was talking about to 3D print stents. And that's how we came up with this in October. And after working on it since then, we've developed several iterations of the data axis, and plan on developing more. Is there anything you want to add to that, Connor? Connor says his Wi-Fi is having connectivity issues right now, but basically we have been working on it since October of 2020, which is to answer your question. Thank you for your question. Do we have any more? All right, I'm going to wait until 2:38 to see if there are any other questions. And if there aren't any other questions at that time, we'll begin to wrap up. I'll wait till 2:37 actually. So. All right, so just in time, another question. What inspired you to do research on this topic? Thank you very much. That is actually a great question. I will speak on my behalf for what inspired me. So basically our roles in this project, firstly, Connor has a huge engineering background and he's sort of taking the lead in engineering in this project. And I have a background in biology and medicine. So I've taken the lead on that biology. Our official titles are President of Medicine and Research for me, and for Connor, President of Engineering and Development. So what inspired me was I've always been very interested in biology and medicine. I actually started doing research in a professional setting at the University of North Carolina, Charlotte, at Chakravarti Lab, and I mentioned him in the acknowledgements. And here I did research in neurology, oncology, genetics, parasitology, and I just developed a love for biology and medicine. So it's pretty much always at the back of my mind, which is why I was able to connect this medical problem after Connor told me about the idea for an innovative motion system. And would you like to speak a little bit about what inspired you on engineering if your Wi-Fi is back up?
Yeah, I think my connection is hopefully working here. Yeah, so I think for me, one of the things is when I actually came up with the concept for the motion system, I was just thinking about different things that have been done within 3D printing. I know that some attempts at polar printing have been done in the past, but they were never designed specifically in order to gain as much precision as possible. So that was an interest that I had working on in the fall. However, I didn't quite have any a particular application for the concept. And then Prabuddha showed me this particular issue in this particular application, and for me, it seemed like it was just a very interesting topic to look into because one, it was an opportunity to actually work on developing this printer, but two, and more importantly, I found it quite incredible that there really wasn't a similar solution currently on the market. There was not a way to really affordably in any manner fabricate stents on site with really any degree of parameterization. And even in off-site options, there were some parameterization options available. However, they were both extremely affordable and they were also limited in some senses in how they were actually able to parameterize the stents. So for me, that was one of the big interests in the project.
Yeah, I think this meant a lot to both of us because we both ventured a new interdisciplinary field of biomedical engineering. Especially meant a lot to me because I was not allowed to conduct wet lab research at the lab anymore because of the COVID-19 pandemic. So that sort of made me shift fields and venture into biomedical engineering research. Thank you for your question. I really enjoyed answering that one. Do we have any more? I'll wait another minute, and then if we don't, then I'll begin to wrap up. All right, it's 2:41, and looks like we don't have any more questions. And on that note, we'd like to wrap up. Thank you, everybody, so much for your time and your very insightful questions. Really enjoyed presenting to you guys today.